Assalamualaikum to the panel examiner. My name is FIRDAUS and my supervisor is TS Cairo Amrin bin Tafaweh. I am here to present my FYP entitled of Development of Low-Cost Motorcycle Linear Warning System using Arduino. As we know, motorcycle is one of the common choice of transportation. In 2017, the registered user of motorcycle is almost 12 million users. Because of many users of motorcycle, the accident rate involving motorcycle also increasing for each year. Motorcycle lack of safety feature thus causing motorcyclists to have a severe danger when involved in accident. Accident statistics have been increased for each year. In 2007 to 2008, the increment is 0.05%, and in 2015 to 2016, the increment has changed to 9.5%. 2015, PDRM has released a statistic of crash by road type. We can see that major of accident happen at straight road type and below than 20% happen at corner road type. Although high number of accident occur at straight road type, but on corner road, many of accident occur in corner road, often resulted in death. Cause of accident divided into three factors, which is human factor, vehicle factor, and environment factor. Human factor contribute to most of the cause of accident. For the accident rate, a countermeasure must be made to make motorcycle alert to their speed and lean during cornering. This project will design and fabricate low-cost motorcycle danger linear warning system using Arduino, and then perform a field test of low-cost motorcycle danger linear warning system using Arduino in actual underbone motorcycle. Scope of this project is the system is only used for underbone type motorcycle, the only used in curved road layout, and the system lifespan is limited to battery capacity. The system will only assist the rider not taking over control of the motorcycle. The Arduino as the microcontroller of the system using low-cost gyro sensor, low-cost GPS sensor, and the analysis will does not consider friction between road and motorcycle tire, assuming that motorcycle and rider has the same lean angle during the corner. Literature review of safe speed during cornering situation is JKR has set a certain speed limit at certain location for the user to operate their vehicle at safe speed. But FND found out that the speed limit set by the JKR was 11% lower than 85th percentile speed. Literature review for lead angle cornering of motorcycle by Carter, Lambon, and Wesley found out that motorcycle can tilt their lead angle at 25 degree with velocity of 67 km per hour on a 76.2 meter curve. Boniolo says that superbike with high performance tire can reach enormous road angle value that is 50 degree to 55 degree. Carter mentioned in his research that novice rider can lean their motorcycle at 15 degree to 25 degree, while experienced rider can lean to 34 to 40 degree. Berg mentioned that ordinary rider in normal riding condition will lean their motorcycle angle not more than 20 degree. Lean angle estimation can be estimated using this kind of formula that has been used by Carter, Cosalter, and Fricker in their research. In this formula, there is a few assumptions that is velocity is steady during the corner, rider lean angle same as motorcycle lean angle, and tire always contact with the road surface during corner. System, Chang and Ng in their research mentioned that the easiest color to be seen is red color. And if the warning alert system is flashing more than 60 frames per minute, then human brain will faster to interpret it as a danger. Begin with component selection and research. After then, the component will be wiring up. After the component finish wiring, the coding will taken in place. If the coding is correct, then the system will function correctly. When the system function correctly, the device will install into a motorcycle and will be done a field test at a predetermined cost. If the predetermined cost data, if the if the field test data has some conjunction with previous researcher lean angle, then it will proceed to analysis. That is being used in this project is Arduino software for coding process, CATIA for designing process, and freezing is used for drawing the circuit diagram. Hardware equipment that used in this project is Arduino Nano as the microcontroller, gyro sensor to measure the lean angle, GPS sensor to measure the velocity, the LCD to show the measure lean angle and velocity, breadboard is to set up the wiring, and a motorcycle is used to done the field test. This is the concept design that has been drawn in the CATIA. The first case contain LCD and the Arduino with the battery. The second case is for gyro sensor, and the two casing is connected using a wire. The sensor location, gyro sensor location, has been proposed a few location, which is under the handlebar and under the seat of motorcycle. And I choose location 1, which is under the handlebar, because the gyro sensor is near the LCD case, so the wire that will be need to connect them both is shorter, thus will save the battery life. The system will use this coding to set it higher or lower blinking rate. The delay function is used to set the blinking rate lower or higher blinking rate. On the left is the top view of the device. We can see the LCD, the blue button as select function, the red button as menu function, the LED glow place, and the on-off button. On the left side is the front view of the device. You can see here is the USB port. Is the gyro sensor with the USB cable to attach to the main casing. And on the right side is the inside view of the main casing. Here is the GPS sensor, 9V battery, USB port, the LED, the Arduino Nano, and the LCD. When the device is turned on, the LCD will show the angle reading, velocity reading, max angle reading, and max velocity reading. This video will demonstrate on how the device is working. So the gyro sensor will be located at the center of the motorcycle, and the main casing will be attached to the side mirror. When the device is turned on, the angle value may be drifted, so a calibration will be required. To start calibrate, the motorcycle first need to be in double stand position. Then press the blue button to open up the menu, and press the blue button again to select between the menu. Press the red button to start the calibration. After the calibration complete, the angle value will show at 0 degree. The field test has been done with correct safety gear. This is the rider view of the device. And this is the demonstrate on how the field test taking place. The station has 5 different locations. The first one is a roundabout at Jalan College Yayasan Saat. The second is a corner at off-ramp Jalan Utem. The third one is at Jalan Tangkak Durian Tunggal corner number 1. The fourth is the same road at corner number 2, and the last location also at the same road at corner number 3. Test average of experiment angle was found keep increasing as the radius corner is increased, and the average of percentage difference between experiment angle and theoretical lean angle is decreasing as the radius corner is increased. So at higher radius corner, the percentage difference of lean angle, theoretical and experiment is decreasing. The first row here is a roundabout testing, and the average of experiment angle was found higher than corner road type because the rider can adjust their lean angle through the corner through the roundabout bit by bit, thus making the lean angle higher than the corner road type. The test velocity has been limited to 50 km per hour, 60 km per hour, and 17 km per hour because if the velocity is lower than 50 km per hour, then the lean angle will be lower than 8 degrees. Thus, it is too small to measure. Also, riding at 80 km per hour in cornering is risky due to the rider inexperience. Also, riders tend to lower the motorcycle speed during cornering, making the 80 km per hour velocity is unachievable during cornering. This is the previous researcher lean angle. From the field test, the lean angle was found around 8 degree and did not exceed 20 degree. Thus, this result has concern with Carter and Berg. But from the lean angle from Lambon and Wesley was not able to achieve in this field test as there is no any component of the motorcycle has made contact with the road surface during the field test. The blinking rate of the device will start giving warning at 15 degree and 15 degree with the blinking rate of 60 frames per minute. Then the rate will be higher at 20 degree of lean angle at 120 blinking rate, and the blinking rate will keep increasing to 240 blinking rate if the leaning angle is more than 25 degree. The price of hardware material that used in this project is RM86.59. The most expensive part is GPS sensor, followed by Arduino Nano and the battery. As a conclusion, the objective of develop and field testing of low-cost motorcycle danger leaning warning system on an actual underbone motorcycle was accomplished. The presented methodology exploits the use of every component thus capable of bringing the reasonable accurate result.